Yeah, so good evening everyone. So we have been discussing on uh, visualization of fields in machines and understanding different machines from electromagnetic, basically magnetic field perspective. So we have reached cage rotor, and the last class we actually started discussing on the cage rotor. Its current, basically we have different bars on the rotor, and which are short circuited from the both from the two sides, and we looked at what happens if we excite only the stator, and what about the flux linkages of different bars. And from first principle, if we know flux linkages of a conducting body, then we also know the induced EMF across that, and from that we got the current also. So may not able to access the erasers and other things. Okay, yes. So we looked at, so to start with we looked at 10 bars on the we have I have indicated 10 bars on the rotor. And what have we done? We have injected sinusoidal three-phase current into the rotor, into the stator basically, and while the rotor is rotating at some speed, say 2400 rpm for this specific case. So we looked at the rotating magnetic field, and you can see, if I stop at multiple instance, now the field is here after a certain time, uh, or here it is not that way, so you have to mark with some conductors. So if I stop here, the field is just ahead of the yellow conductor here. Now if I go ahead, then after a certain time you'll be able to see that the yellow conductor keeps on lagging, keeps on getting lagged from the field. So now field is here, yellow conductor, you can see that it has gone further away from the field. So that means that there will be some change of flux linking each and every bar. So that has been plotted, and we also understood that what do we mean by flux linkage. If there is any conductor, and if any flux line is enclosing that, that means it is linking that conductor. For this case it is the bar. And if we have some flux line like this, say this is a flux line, the second one that I have plotted, that is not enclosing the conductor, that means this flux line is not linking that conductor, as simple as that. So I have plotted in a flux linkages of 5 bars. You can see that uh, this is how they look, and they are basically phase shifted from each other, and the frequency is basically corresponding to 100 millisecond, that is 10 hertz. 1 by 100 millisecond, that corresponds to 10 hertz. So 10 hertz, what is 10 hertz? 10 hertz is basically the 10 hertz corresponds to 600 rpm. What is 600 rpm? We know that the stator field is rotating at 3000 rpm, rotor is rotating in the same direction at 2400 rpm. So 600 rpm is basically the relative speed of the rotor conductors with respect to the stator rotating magnetic field. So that is why we have 10 hertz of flux linkages on each and every bar. And all the bars, suppose this bar is located at this for this time instant, this bar is located at about 90 degree, and the next bar, colored bar, is located 3 slots ahead. That is, if we have 30 slots here, so 360 degree divided by 30, that is basically 12. So 12 into 3, 36. So all if those are plotted, if flux linkages of different rotor bars are plotted, we expect that they would be phase shifted from each other by 36 degree. And if actually all the flux linkages of all the bars are plotted, because the angular displacement is 12 degrees, so it will be 12-degree phase shifted from each other. So because it's a linear system, there is what do you mean by linear system? Whatever is the, if we excite it by certain frequency, it will, the output will also be of the same frequency. So if uh, still now it is not that flux linkage, how to get induced EMF from that, we have to just take a differentiation of that. Differentiation of flux linkage to get the induced EMF. And induced EMF into some voltage, applied voltage to current, they are basically the linear system theory comes in. If it is a linear system, we expect currents of the, if the applied voltage has certain frequencies, the output is will also have those same frequencies only. So we expect that if we, because we have induced EMF, induced voltage across each bar at of 10 hertz frequency, so if there is some current flow, there they will be of the same frequency. Next we looked at different instance. So first instant I discussed in detail, like we stopped at a instant, and at that instant this is the field. Now I try to indicate different flux lines, and whether that how many flux lines are basically enclosing one particular conductor or bar. So we saw that this bar 13, because it is exactly at the axis of the magnetic field, so no flux lines is actually enclosing that. So bar 13 has zero flux linkage at that instant. And if we take differentiation of that, then if it is sine theta, then differentiation of that will be cos theta. So if there is a zero crossing, where the value is going from negative to positive, then you expect that it will be cos. So the peak will appear there. So this is about the flux linkages and induced EMFs that I have discussed. And if you look at different bars, say B19, you can see that all this, only leaving this line which is there, this line is surely not linking B19 or the next one, that is B22, but all other lines, say this line is also enclosing B19. Then if I go further and further, all lines are enclosing B19. That means B19 will have a significant flux linkage. So B19 is the magenta one. You can see that it has a significant flux linkage. And why negative? We have discussed that because here, if I go back to the earlier case, where I have considered positive direction to be out of the screen, that is dot. So dot is considered the positive direction for all bars. So if it is dot, if dot current flows, then the flux lines will be like this, which will be enclosing it in the anti-clockwise direction. So if any flux line encloses a conductor in the anti-clockwise direction, then we will call it positive flux linkage. And if the same bar, if it is enclosed in the clockwise direction, then we would call it as negative flux linkage. So because uh, here at this instant, uh, here at this instant, what is the direction of the field direction has been indicated here. So flux lines are basically clockwise in the upper half. So all the upper half bars at this instant will have negative flux linkages, that you can see. B19, B19, B25, B19 and B25, B19 and B25 both have negative flux linkage at this instant. whereas all the bars which are on the lower side like B1 and B7 they are having positive flux linkage because flux lines are going in the anti-clockwise direction in the lower half. That is why flux linkage is positive. So how do we get induced EMF from flux linkage? That is also clear. I have discussed it in elaborately last class. So then we went on to discuss about currents. So we looked at each bar. So this is say a copper bar or aluminum bar where there is some induced EMF. Now you can understand that this will have some cross sectional area. This has certain length L. This will have some cross sectional area A, and this material will have certain resistivity rho also. So rho L by A, that is basically the resistance of the copper bar, and there will be additionally some inductance also. Why inductance? Because if you have any copper bar or any for that matter any conducting thing, if some current flows, then there will be some magnetic field around that, and that magnetic flux lines will be enclosing that conductor, enclosing that bar, conductor, strip, whatever conducting body we have. So if there are some flux linkages, that means there are some flux lines, that means those flux lines will be linking that conductor also. That means there will be some flux linkages inevitably for any conductor, and the flux linkage will scale to current. If suppose you pass 1 ampere of current, whatever will be the number of flux lines it is enclosed by, if you inject 2 ampere of current, it is supposed to double if it is homogeneous medium like air. If it is in air or in a magnetic material with constant permeability, it is supposed to double. So the ratio of flux linkage to current, that is defined as inductance. So that is why all conductors will have certain inductance, because if some current flows to that, there will be some magnetic field, and magnetic field will cause some flux linkage, and inductance is defined as the ratio of flux linkage to current. So all the rotor bars will have certain inductance affiliated to it. So we have now if we have to represent the electrical equivalent circuit of a bar, then how do we do that? So we understand there will be certainly some resistance, we understand that there will be certainly some inductance. Then whether they will be in series or parallel, that is the question. So this resistance will cause what will it cause? It will cause some, if some current flows, then there will be some copper loss, there will be some losses, and that loss is measured by the voltage across it into the current. So that means there will be some voltage across the resistance which is responsible for the power loss for some current flow. And similarly, uh, there, if say there is some current flow through the bar, say I. So this current I square into R, that is responsible for the power loss. And if some current flows through a conductor, then there will be magnetic field, and there will be energy stored in magnetic field. What is that? That is half L I square, which is also dependent on the current. So yeah, if we see the same current that is responsible for the dissipation in the resistance, that same current is responsible for the induced EMF or the energy storage in the magnetic field also. That is why if we have to represent this L and R as a equivalent representation of the of equivalent circuit of a bar, then we have to connect them in series so that the same current, same bar current flows through both of them. That is why we saw that we represented each bar with certain resistance and some inductance, and there is some induced EMF across this bar. So these are the two terminals of the bar, say. So we have seen what is the induced EMF. So this is the induced EMF across this bar. So this is the induced EMF, say EB. Now, what will be the current if it is RL circuit from phasor, simple phasor? If there is some voltage, then current will lag it by certain angle, and the impedance will decide what will be the amplitude of that. Now, if the resistance is 0 and it is purely inductive, then the current will be lagging it by 90 degree. But on the other way, if inductance or resistance is very significant compared to the omega L, that is inductive impedance, then it can be considered to be purely resistive, and the current will be almost in phase with V. So in this case, we have seen that the induced EMF, that is at the slip frequency, and slip frequency is FSL is equal to S into Fs. So slip is typically point 1 or less than that, and Fs, if it is 50 hertz machine, then 50 into point 1, or even 0.01, 0.02, whatever. So you can, for typical cases, typical cases, this slip frequency is actually very low, and even lower than 1 hertz. So for all these cases, the inductive impedance is very low, so the resistance actually dominates over this inductance. So resistance is very high compared to inductance. That is why wherever we have peak induced EMF, we can assign positive, or the peak current through that. So that is why bar 13, because it has positive induced EMF, peak induced EMF, so I have assigned positive dot, and here negative dot of the highest magnitude, and accordingly there are other currents. Now if this is the current distribution, how will be the field of the rotor? We have seen that we have a field like this, and by looking at the air gap field distribution, we have come to a conclusion that the stator field is leading the rotor field in this case. That corresponds to the motoring operation. So there is another way of looking at that also. Like, if we assign, so one way is we can look at the air gap flux density, and if it is radially outward, we'll assign positive sign towards it, and if it is radially inward, then we can assign negative sign towards it. And then if we plot b theta along the air gap, b for the stator, b for the rotor, then we can clearly say that which one is leading and which one is lagging. And another simple way can be there. So if so suppose at this instant we the stator field is shown by this. So what is this arrowhead is basically, what is it connecting? It is connecting the north to south, so it is indicating the direction of the magnetic flux lines. So similarly, the south and north are here. Then if we do the same thing, that is, if we connect north to south, then north to south, that is here. So we can see that this is the rotor field and this is the stator field. If we this FR that I have indicated, that is not the rotor flux direction. Earlier arrowhead indicates the rotor flux direction. This is the magnetic field uh, uh, thing, magnetic field direction, considering the same thing. That is, if we start from north and end at south, the arrowhead, then we have to represent the same thing for the rotor also. And if we actually do that, then the field direction comes here, and as the rotor is rotating in the anti-clockwise direction, you can clearly see that the stator field is ahead of the rotor field. So energy transfer happens from the stator to rotor. Now I quickly rush through the other few instances also, like this t equal to 15 millisecond, where the stator field flux direction is basically here almost at theta equal to 270 degree. So in this condition you can see that earlier B13 was here, now B13 has come here. Now there are some flux lines. For an example, this is one flux line. So there are actually a lot of flux lines which are enclosing this B13, but this flux line, for an example, is not enclosing B13. So you have some flux lines like this which are enclosing B13, and you can look at the direction also. If flux line direction is like this, so that means here it is going uh, like this in the anti-clockwise direction. So B13 is supposed to have positive flux linkage, as you can see here at this instant. And whatever from geometric symmetry, you can see that whatever is the flux linkage of B13, that same will be the flux linkage of B1 also, and of the same polarities. So that same thing you can see here, B1, that is the red curve, and B13, that is this blue curve. They are having same flux linkage at this instant. And which one is having the maximum flux linkage? You can see whichever conductor or bar is there perpendicular to the magnetic field axis, that will always enclose the maximum number of conductors, maximum number of flux lines. Basically all the flux lines will enclose that. So B7 is having the peak flux linkage, as you can see at this instant. So similarly, flux linkages of B19 and B25, they are negative, and they are also from symmetry. You can see whatever is the flux linkage of B19, that same has to be the flux linkage of B25, because if I draw a line perpendicular to the magnetic field axis, B19, if it is at some theta, B25 is at the same theta. So they are symmetric with respect to each other. That is why they are having the same flux linkage at that instant. So if we know flux linkages, same story, we can get the induced EMF also. And here at this instant, this is the stated flux direction, and the corresponding currents are also indicated. So if dot currents are there on the top side, and cross currents are there on the bottom side, then the rotor flux direction will be right hand side, as I have shown, as I have indicated in this figure. So yeah, from this case also you can see that if we connect north pole to south pole for the rotor, if we stick to our same definition, north pole to south pole, that is the stator field direction. So north pole to south pole, that has to be the rotor field direction also. So and the rotor is rotating in the anti-clockwise direction, so obviously Fs is leading Fr, and same thing can be seen for 20 milliseconds. This is exactly the opposite thing what we saw at t equal to 10 millisecond, because at t equal to 20 millisecond the field direction has flipped. Earlier field was at theta equal to 180 degree, now field is at theta equal to 0 degree or 360 degree. So whichever uh, so at this instant again, so earlier case, all the conductors, all the bars on the top side were having a negative flux linkage, but because now field direction has changed or flipped 180 degree, flipped by 180 degree, so all bars, which that is B7, B13, you can see that B7 and B13, that is the yellow green and blue, they are having positive flux linkage. Green and blue, basically these two, these are having positive flux linkage. B1, that is having zero flux linkage. And again all the bars on the bottom side, B19 and B25, they are having negative flux linkage. Similarly, we can derive the induced EMF, and accordingly we can assign sign for the currents, and we can have the rotor flux direction also. So this is what we discussed, we rushed through at the end. So I indicated that we will learn how to so this is about the bar current. So you can see that at any given instant, you have from this analysis you can get what will be the bar current. Firstly, bar induced EMF. Now next, if you can calculate the resistance, neglecting the inductance, it is possible to calculate the bar currents. So for some indicative thing, so here you can see that at in each bar the induced EMF is in the order of say zero point 0.5. The peak is of the order of 0.5 volt. Now let us take some values, like if say 1 bar resistance is say how much, it will be very low, say tens of milliohm, not more than that, or even lower than that. So if it is say 10 milliohm, just an indicative number, say 10 milliohm, then what will be the bar current? Bar current will go as high as this is 1000, 5000 by 10, that is 500 ampere. So as high as 500 ampere peak may flow through the bars. So yeah, bar sizing has to be appropriate so that they can carry that amount of current. And this can be looked at from another perspective also, like uh, why bar current should be so much higher. uh, Probably we'll discuss it after I go through how to get the end ring current. So say we know the rotor bar currents. So how are rotor bars connected? Say I'll indicate only say 5 or 6 bars for this is the end ring, this is the short circuiting end ring. For this case, say our bar 1 is coming and getting connected here. Now let us say we have bar 2 connected here, say bar 4 connected here, and bar 3 connected here. They are connected, they are actually coming and getting connected at these locations, right? Now you can see that we have 4 segments in the N ring. So it is basically like this. Some current, say this is the bar, say this is the direction of the positive current, and we have two side by side end rings, which are basically these two, which are connecting this bar to the next bars. So uh, say some current, say if it is bar 1, so say IB1 is flowing through this bar, and you know what is IB1 as a function of time. That you have information because you have induced EMF as a function of time. If you simply divide it by the resistance, bar resistance, you also have bar current, that same bar current as a function of time. Now uh, let us indicate some direction of the end ring currents. So say all cases entering current. So this is entering 1 IE1, this is IE2, IE3, IE4. All these are your entering currents. Now what comes to your mind? You can apply KCL, right? You have this one, say this bar, and you have two entering segments connected, say IE1 and IE2. So you have one node, and in this node you can apply KCL. So whichever is approaching the node, so IB1 plus IE2 equal to IE1. So you have IB1 equal to IE1 minus IE2. So you have one equation for this node. So similarly you can apply KCL and uh, get these many KCL, these many equations. So you can so after you get the equations, then if you get it for the 4 bars, you will see that we will not have 4 independent equations. Basically we would have basically n minus 1. If there are n bars, then we would have n minus 1 equations, because finally it's a ring. So we would have n minus 1 independent equation, and what will be the nth equation, because we have n unknowns, that is the segment currents. So we have, so in perfect balanced case, or normally we must have the voltage, because this is forming one loop, this end ring is forming one loop. That is why if we apply KVL in it and say R1, R2, R3 and R4, they are the corresponding resistances of these end rings, that is of these of this uh, ring segments. Then if we apply KVL, then it is 0 equal to IE1 into R1 plus IE2 into R2 plus IE3 into R3 plus IE4 into R4. Now in the symmetric case, if all the resistances are perfectly equal, then that basically boils down to summation over IE, where in where I runs from 1 to n, that is basically 0. So this is your nth equation. So earlier you had n minus 1 equations, and if you solve this, then it is possible to get the currents of these different segments of the end rings. So this is how end ring current calculation can be done. And actually, while you are designing some machine, you have to get the rotor bar currents, and you have to size your rotor bar. You have to provide appropriate cross sectional area to the rotor bar, so that there is no overheating in the bars. And accordingly you have to short the bars. It does not mean that you short it by any means. You have to provide, you have to calculate what is the current that is going to flow through that short circuited ring, and appropriately its thickness and other dimensions have to be decided. So this is about calculation of end ring currents. So I will briefly stop here. Is there any question?
Samrat, I have a question in slide 48 before you started this one. Huh.
Okay.
Yeah, maybe you can stop here also.
48.
Yeah, this is fine. This is fine. So here the flux lines direction you have shown, right? It is going in maybe clockwise direction on the for the top bars.
Yes,
Correct.
yes.
So if the polarity that is marked as north and south, is it correct? Because the flux line coming out is usually north, right?
No, no,
So
this is the north and south of the stator surface. So this is the
yeah, so
stator
that is where I
surface.
got confused. So
Yeah, so you can see that it is the stator surface where this north and south are indicated for the stator. So if this is the flux direction, so if this is the stator surface, then it is entering the surface, right? It is
but the
entering the
magnetic
surface here.
field is also of the stator, right? So I think in
Magnetic field
one
is
of
of
the
the stator. Yes.
yeah, so I think in one of the early classes, I think they marked it opposite. That is where I got confused.
No, no, no.
It
This
is,
is at 10 equal t equal to 10 millisecond.
I mean, I
So
think the
if it
time
is,
doesn't matter. So wherever
no,
this is,
with time it will flip.
okay, correct, correct.
So
Huh.
at t equal to 0 millisecond or t equal to 0, it will be, the flux direction will be here. So this has to be south and this has to be north.
Okay, okay, okay. So
Now
this is at
because it is t
halfway.
equal to, yeah, yeah, this is at the halfway, that is why it has reversed.
So without knowing the time, is there a way to know this direction or?
Actually, if we plot the field, then we can look at the direction of the flux line also. I have not indicated it here, but
Okay.
B will have certain direction, right? So all
Yeah.
these lines will come with some arrow, so it is possible to get to know that.
Okay. So because it is at 10 milliseconds, so we are already in the other half direction. So
Yes,
this has
yes,
okay.
yes, yes, yes.
Okay, one more question is how maybe you can stay in the previous slide only. So here when you were telling about the direction of EMF
Huh.
or yeah, I think the which one should I tell? I think when you were talking about this B19 and B22, Uh, I think the flux linkage of the bar 19 and bar 22. You said the
Yes,
flux is rotating in this direction and we have considered a dot. But right now we have not put any dot polarity, right? So the
no,
dot polarity was coming after this uh, when we were looking at the currents induced. So
correct.
that is one more clarity I want.
Okay,
You got
so
the question? There
yeah,
was
yeah, I
no.
got the question. Suppose we have any circuit, any electrical circuit, say some
Yes,
source, some EMF source we have, some
yeah,
resistance we have, some inductance we have, anything we can have. Now we will always assume some direction of current to be positive, right? So say
correct.
we assume this direction of current to be positive. So if this is the positive direction of current, then we look at, okay, what is the current. So if it is actually flowing in this way, then it is positive, and if it is actually flowing in the opposite way, then it is negative. Similar to
Correct.
this, we have assigned a reference direction for the current. So dot
Okay.
polarity of current will be considered to be positive, and dot polarity of current, whatever flux linkage it produces, that will be considered positive, because dot polarity of current will produce flux linkage, flux that is rotating in the anti-clockwise direction. So
Yeah.
that is why we consider that, okay, if flux linkage is in the anti-clockwise direction, that we will consider as positive flux linkage.
Okay, so everything is considered dot initially,
Everything is, yeah.
and then we looked
Yes,
at the flux linkage and then corrects. Yeah,
yes, yes.
understood. Thank you very much.
Yeah, thank you.
Yeah, Samrat, can you go back to some 47 slide number?
47, yes.
Yeah, here, please let me know if my understanding is correct or not. I can
Yes,
realize the flux linkage in two scenarios, but the two scenarios are going to give the same results, but the uh, realizations will be different. My first scenario is uh, in the stator, if the RMF is produced, it will rotate at some speed.
yes,
Let's say 3000 RPM. So the rotor has some bars and it is rotating at some speed. Okay.
yes,
Suppose you say, as you said, 2400 RPM.
yes,
The field in the rotor bar will be rotating at 600 RPM with respect to rotor.
with respect to rotor, yes,
So the flux linkage will be realized in that way also. The other way is that if I keep the rotor as a stationary, consider the rotor as stationary, and I can
yes,
realize with 3000 RPM.
yes,
That's the other way, right?
yes,
Yeah, yeah. Okay. This is my clarification. Is
yeah,
that
yeah,
right?
yes, that is correct. That is what I discussed initially, right? If I briefly go back, like we looked at two cases. Uh, One, what is happening if, yeah. So initially we looked at two cases, right?
Yeah.
Where we kept the rotor stationary and then looked at the flux linkage of the rotor, of the bars or conductors of the rotor, and we saw that, yeah, actually if the rotor is stationary, then there will be 50 hertz, that is same frequency of stator, that 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 frequency flux linkage. And if
Yeah.
there is that frequency flux linkage, that means the rotating field that will be generated due to the rotor currents will be rotating at 3000 rpm only. So there will be torque production.
Okay. Yeah.
And the other way is what we discussed next is, if the rotor is rotating at 2400 rpm, then the relative speed, as you told, is 600 rpm, rightly. So that case also we can have,
Okay.
we will have two fields which will be, both will be rotating at 3000 rpm, so there will be torque production.
Okay, Samrat. Thanks.
Okay, thank you. Anything else, or we will go to the generation case? Should be very interesting.
And one more clarification. In the
Yeah,
question which was asked by Roja,
Yes.
I think she is confused with the DC machine, right?
Uh, what do you mean by that?
Because the poles will be fixed on the stator,
Yes.
north and south
Yeah,
will
yeah,
be
yeah.
named.
That is correct. So DC
Uh,
machine, there is once we inject some current, that means field direction does not change. It remains the same. So
yeah,
that
yeah.
means north and south also remains the same. Remains the same. If it is entering, that means it is south. If it is leaving out from there, it is north. But in
Yes,
this
yes.
case, we have north and south, but that is rotating. That means if it is at time equal to 0, then wherever the north and south poles are,
Hmm.
at 180 degree, omega t equal to 180 degree, it will flip. It will become opposite. And it actually continuously rotates.
Yes, yeah.
Yeah. Okay. So let us take this case. Let us see what happens. So yeah, in this case, we are looking at the exact same scenario. We are making the rotor to rotate at 3600 rpm. That is more than the speed of the stator magnetic field, right? And we are looking at the flux linkage and induced EMF in the rotor bars. First we will look at the animation where the rotor is also rotating and the stator field that is also rotating. So I'll start that. Yeah. So you can see that I'll stop and show you more clearly. You can first just look at the animation when it is rotating. Now probably because in video or during this mode of presentation it may be difficult to see animations, because anyway there will be some lag uh, during this presentation. So I'll stop at multiple instance. Say I stop here. Now what do you see? The field is somewhere here. I don't know whether it is this is the direction or the opposite is the direction, because I have not indicated the flux lines. So let us start from the beginning. So here I know that the field is actually in this direction, right? So it is at the it is crossing, it is cutting the yellow conductors as well as the pink conductors. Now as I go ahead by some by some rotation, you can see from the same location, that is says theta equal to 0 degree, because the field has some velocity, say 3000 rpm. So within in same time, in time duration 2.8 millisecond, the field will rotate by some angle, say theta 1, and the rotor will rotate by some other angle, theta 2, because omega 1, that is say omega s, that is the stator rotating magnetic field speed, and rotor as certain omega r, that is the rotor mechanical speed. If rotor mechanical speed is greater than stator speed, then rotor will move ahead. That is what you can see here. At this instant, the field has moved by this much angle. So it has moved by some angle and it has reached here. But the same yellow conductor, because the rotor is rotating at the higher speed, so it has moved ahead of the magnetic field and it has reached here, right? So the rotor has moved by this much angle. This is higher compared to the movement of the stator magnetic field. So this same thing you will observe as I go on running the case. The same yellow conductor will start moving ahead of the more and more ahead of the stator magnetic field, right? This is one observation. In the earlier case, it was the opposite way. So the magnetic field was moving ahead of the rotor conductors, and that is because the rotor mechanical speed was lower compared to the stator this rotating magnetic field speed in the earlier case, but here in this case rotor speed is higher. Now what is the impact of that? If I look at the flux linkage with time, flux linkage waveforms basically with time, let us briefly go back to the earlier case and observe that. So in any case, say I stop here. I stop here at this instant. Let us try to see uh, which one is leading and which one is lagging. So if I start with this one, say this green one is bar 7, bar 7. The next one is bar 13. So that means bar 13 flux linkage is lagging the bar 7 flux linkage, and similarly next is bar 19, next is bar 25, next is bar 1. So the sequence, if I tell in that sense, it is 7, 13, 19, 25, 1, 7. This is the sequence. This is the sequence of um, the flux linkage in from leading to lagging. So this becomes a sequence. So say for an example, if it is only 3 phases, say wound rotor machine, it will be some RYB or something RYB, say. Now in this case, can you look at what is the sequence? So say this one we take as reference 25. What is the next? Next is not 1, but it is 19. Then it is blue one, that is 13. Then it is the green one, that is 7. Then it is the red one, that is 1. So here the sequence is 21, 25, 19, uh, 13, 7, 1. So it is the opposite sequence compared to the earlier case. So that means in this case, if we have, suppose if we had 3 windings on the rotor, and for the motoring case the phase sequence would be R Y B. For generation case the phase sequence would become R B Y. So the phase sequence would change. In this case also you can see that in the bars, because we have I have plotted 5 bars here and total is 360 degree. So 360 divided by 5, that is 36 degree. They are phase shifted from each other by 36 degree, and this is the sequence. And if we know flux linkage, then the induced EMF also can be obtained, and they are of the same sequence. You can see that it is 19, then 13, then 7, then 1, then 25. The same sequence whatever we observed in the flux linkages, that same thing is retained in induced EMF also, and same thing will be retained in the currents also. Now if we have distributed winding, and if we inject sinusoidal currents of some phase sequence, say RYB, we saw that it rotates, the magnetic field, equivalent magnetic field rotates, and it rotates in the anticlockwise direction, say. Now what is expected to happen if we inject sinusoidal current, balanced sinusoidal current of the opposite phase sequence? Then it would rotate in the opposite direction. That is why in induction machine, if you give some RYB, some phase sequence 1, if the rotor rotates in anti-clockwise direction or some direction, if you change 2 lines and connect it and give supply again, then it will rotate in the opposite direction, because simply the speed direction of the rotation of the magnetic field is getting changed, right? So in this case let us try to see. one by one what happens. So in this case again we are at t equal to 10 millisecond, that is why the field is here. And if we look at the stator surface, then here in this surface the flux lines are entering, that is why this stator surface is south pole. And here in the stator surface the flux lines are coming out from that, that is why we have north pole here. And at this instant we have all these different bars whose flux linkages are plotted or reproduced from the earlier figure. And the idea of flux linkage remains the same, that is B7 at this instant also will have zero flux linkage, and similar to the earlier case only. And accordingly we can have the induced EMF, uh, we can have the induced EMF at this given instant. And if we know the induced EMF, then we can assign dot or cross polarity for the current in the bars. Like in this case, what do we have to provide? We have to give for the pink one and black one, that is 19 and 25, we have to provide dot polarity. And for the other cases like the bar 1, bar 20, 13 and bar 7, we have to provide negative, that is cross. So that same thing has been given here, 7, uh, so 19 and 25. So 19 and 25, where is 25? 25, they have been assigned dot polarity of current. And 7, you can see 7 is basically the peak induced EMF, so I have to indicate it by a thick cross mark. And the others are having some negative of equal value, so that is why it is B7 has been given with thick cross mark. And the others like the B13 and B1, they are given some cross currents. And 180-degree opposite, the opposite thing happens. Like if B7 is here, then the opposite bar must have the peak positive current, peak dot current. And same thing for all the rotor bars. And this is the current direction. If the rotor flux direction is now indicated, because these are dot, the left hand side conductor bars are having dot current. So again applying right hand side rule, you can see that the thumb points upward. Thumb points upward means upward will be the direction of the flux lines because of rotor. Now we have to look at the rotor surface. From the rotor surface, on the top side flux lines are coming out, that is why the rotor surface is having north pole and the stator surface is having south pole. Now if you remember the what was there in the about the field polarity at t equal to 10 millisecond for the earlier case, that is when speed was 2400 rpm, it was the opposite. And if I plot the field like the way we plotted last day also, theta, so this is 180-degree, this is 360-degree, obviously 0-degree, 90, 270. Now let us plot for the stator first. So at 0-degree we can see that the flux direction is right to left. So in this air gap it is radially inward. If it is radially inward, I have to assign negative sign towards it to it. So that is why I am indicating with this line. Now if I go to the theta equal to 90-degree, it is exactly 90-degree to the field direction. So there is no field, basically it is 0. If I go to 180-degree, theta equal to 180-degree, that is here the stator flux, that is radially outward. So 180-degree it is having peak field, and again 270-degree it is having 0, and 360-degree it is coming back to negative peak. So this we have seen how B distribution along air gap look like. So this will be sinusoid, and of course due to the slots and other slots, basically the presence of slots, there will be some notches on the B uh, uh, not positive notch but negative notch only, some negative notch on the B. So uh, okay, if it is a fundamental, it can be positive as well as negative notch. Anyway, those are details. So anyway, let us not worry about the notch, but our stator field will look like this, along the air gap. Now if I try to draw the same for the rotor, at 0 degree we have 0, at 90 degree the rotor flux is radially outward, so we have to assign positive sign to it. Again 180 degree we have 0, 270 degree we have to assign negative sign to it, and 360 degree again 0. So the fundamental uh, field will look like this, and you can see that in this case the rotor field, where this is the stator field, the rotor field is leading the stator field by 90 degree, and that tells you that it is a generating action that we are having, because power flow is happening from rotor to stator. That is what happens during generating action. Now the same thing can be seen at uh, 15 millisecond, about 15 millisecond, that is 14.8 millisecond what I am showing here, because I have done simulations at discrete time steps, so 15 millisecond I did not do, so that is why I have to stick to 14.8 millisecond only. So the field direction is like this, the direction is downward. So south and north pole appropriately, accordingly we have flux linkages of the different bars, induced EMF of the different bars. So with that same argument, if we assign sign towards that, you will see that um, uh, cross and dot current polarities, and the rotor flux will be as indicated. I would draw for all cases for you to visualize how the field is moving. So this is 0, this is 180, this is 360, 90, 270. Now if I try to draw for the stator, here 0 degree is 0. Now 90 degree the flux is downward, so it is radially inward, that is negative. Now here 180 degree 0, 270 degree it is radially outward, so I have to assign positive sign, and 360 degree again it is 0. So this is the stator field, and if I draw the rotor field at 0 degree, what is the rotor field? Rotor flux direction is right to left, so here it is radially inward, so of course it is negative here. Then 90 degree it will be 0, 180 degree it will be positive, 270 degree it's 0, 360 degree it is again negative. So if they are joined with the indicating the fundamental sinusoid, you can see that here also the rotor field which is indicated with red, while the stator field is indicated with the blue one, rotor field is leading the stator field, and same generation action. Same thing the last instant for induction machine, it is t equal to 20 millisecond. So again at this instant, same flux linkage and induced EMF. These are about the current polarities and the rotor field, of course. Again, if I plot the same thing, 0, 180, 360, 90 and 270. First plotting the stator. This side it is radially outward, I have to assign positive. 90 you know it will be 0, 180 you know it will be minus negative maximum, 270 it is 0, and 360 it is positive maximum. So this is the stator field, this is the stator field. And if the rotor field is plotted, so here at 0 degree it is 0, 90 degree flux direction is downward, so here it is radially inward, so I have to assign negative sign to it. Then 180 degree it is again 0, 270 degree radially outward, so positive, and 360 degree again 0. So this is the rotor field, and again you can see both the fields, these are traveling in space, while the rotor one is leading the stator one by 90 degree. So you have torque production, uh, and this is the perfect scenario for torque production, because uh, uh, if we have two fields, if the relative displacement is 90 degree, because the torque is basically proportional to the sine of the angle between the two, so delta if it is 90 degree, then we for that given field we can have maximum torque production. So induction machine in that sense, if it operates very close to the synchronous speed, that is uh, nearby synchronous speed, say 2900, if it is a 3000 rpm machine, 2970, often it will rotate at very low, very um, close by speeds, very close to the synchronous speed. So uh, most often it is the delta angle is most often very close to 90 degree. But unlike this, in the synchronous machine we won't have this delta angle to be more than 20 30 degree, because otherwise it may go out of synchronism, and there may be instability because of that. So synchronous machine we have to stick to very low delta values, but induction machine actually we can if it rotates at very close speeds very close to synchronous speed, then we can have 90 degree, which is ideal for torque production. Now I would uh, just conclude with one possible way of analyzing why rotor bar currents can be so high. So typically when you draw the steady state equivalent circuit of induction machine, you would draw like this. So uh, you will refer everything to the stator, and then you have some input supply, then you will have the stator resistance, you have the stator leakage inductance, then you will indicate the magnetizing inductance as well as the core loss branch, if any, if you want to indicate that. Then of course you will have the uh, leakage inductance from the rotor side, and the rotor resistance, and you will have the resistance that represents the energy transfer, that is the power transfer from the mechanical power converted from electromagnetic power. So that is the stator side, or the equivalent circuit of the steady state equivalent circuit of the induction machine, by referring everything to the stator. Now we can do it in a different way also, like that is very commonly done for synchronous machine. The same thing can be done for induction machine also, just for the sake of discussing this. So if you consider any of the windings of stator, just the way we had some flux linkages of the stator winding, of the rotor bars or rotor winding, similarly there will be some flux linkage of the stator winding also, and the flux linkages of the stator winding will also keep on changing. If I consider the net field, say for this instant, if I go to one of the animations, where is the animation? Yeah, so this is one of the animation. If I run this now, do not focus on the rotor, but focus on the stator. So this is the, this say R phase, say this is the R phase axis, and this is the net field, this is the net field axis. Now at this instant of time, you can see that a lot of flux lines are actually enclosing the rate phase conductors. Now if I go ahead and probably go here, you'll be able to see that actually there is no net flux linking the R phase conductors, because whatever flux these two conductors are enclosing, they are also enclosing in the reverse direction for these two cases. So here if it is clockwise, here it has to be anti-clockwise, so net there is flux linkage equal to 0, right? So next, if I move ahead, at this instant where the R phase axis is aligned, or the magnetic field axis is aligned to the R phase axis, so all the flux lines which are flowing here are enclosing or linking the R phase conductors. So similar to what I have plotted for this case, that is flux linkage for the rotor bars, or if there are windings, flux linkage for the rotor windings. Similar to this, it is possible to draw flux linkage of the stator windings also. And if there is some flux linkage of the stator winding, there will be some rate of change of flux linkage of the stator winding, and that is nothing but the induced EMF of the stator winding. So electrical equivalent circuit of the stator for induction machines also can be indicated by some induced EMF, say E1, and we are giving some supply, say V in, and there will be of course some resistance of the stator winding and some leakage inductance of the stator winding. What do we mean by leakage inductance? Leakage inductance means this corresponds to some flux lines which are not linking the rotor. That is, say we have some conductor, we have this conductor of the of the stator, some current is flowing through that, some flux is also flowing like this, enclosing the rotor completely, which are not crossing the air gap. So these are leakage lines for the stator conductor, and similarly there are leakage lines for all these stator conductors. So all these correspond to this leakage inductance of the stator winding. And beyond that, what is this? This is the induced EMF in the stator winding, right? So this is how you can represent the an induction machine. Also, it is not necessary that you have to always go to the equivalence steady state equivalence circuit and you will apply power balance theorem, and then you will indicate the power transfer by some dissipation, by some dissipative element in form of a resistance, and whatever is the current, that current square multiplied by this resistance, that is the electromechanical power transfer. It is not necessary to model it always like that. You can also model it like this, where this is the input current and say this is the induced EMF E1, instantaneous quantity, so I will indicate with small letters. This is R resistance, some leakage inductance, and there is this induced EMF. So instantaneous power transfer that happens to the air gap, or basically the air gap power, that is nothing but E1 into I1, and that is a power phase equivalent circuit. So if you have E2 I2 plus E3 I3, that is the total three phase power that goes into the air gap, that is your air gap power. And where does this air gap power go? This air gap power goes to the rotor. In what form? It goes to in a form of the induced EMF in the rotor, because we are not giving exciting the rotor with any active source. We are not connecting any voltage source, three phase AC voltage source, to the stator. So what is the source? If some current is flowing in the rotor, what is the source of that? That is the induced EMF. Whatever we have seen, the bars will have induced EMF, and that is this induced EMF. That is, say, for simplicity, let us consider the case for the wound rotor, and say it is the induced EMF E2 of one of the phases. Now again, all the rotor bars will also have some leakage inductance. Means if we have a rotor bar like this, there will be certainly some currents which will flow only enclosing that bar and will not cross the air gap to cause flux linkage of the stator winding. So that is what we is known as the leakage flux. So there will be inevitably some leakage flux of the rotor also. So some leakage inductance. Basically the leakage flux will is responsible for some leakage inductance, and there is some resistance of the rotor bars also. So this voltage we have seen this voltage induced EMF and this inductance and this resistance. So there will be some current flow in each of these windings of these phases. Basically if it is bar, then there will be some currents through the bars. And this is how this is the rotor side model, the rotor side electrical equivalent circuit model for the induction machine. Now what is the energy that is getting dissipated? You can see that energy is basically, if this is I2, then the energy that is coming to the rotor is E2 into I2, right? Obviously these are AC quantities, so we have to ideally we have for active power calculation we need to consider the power factor angle also. As of now, let us ignore that. Power factor angle will be significant in stator side, but not that significant on the rotor side, because again whatever discussions we had. So E into I, E1 into I1, that can be approximately written as E2 into I2, from because this is the same air gap power that is coming and uh, flowing in this case. So this induced EMF is typically uh, having a fraction, or a fraction lower than the induced EMF in the stator because of the slip. So induced EMF in the rotor is slip times the induced EMF in the stator, and slip is typically very low. So from this equation you can see that the I2 is basically E1 by E2 times I1, and E1 by E2 is basically 1 by S into I1, and S being a very small number, so I2 is actually expected to go much higher compared to I2. That is why those numbers, say 500 ampere, 400 ampere, whatever we saw for some indicators, for some induced EMF and some indicative resistance of the bars, those are not impractical values, but that is what is expected in the bars of an induction machine. So probably I'll stop with this point. Next we'll, so enough of introduction of the entire machines. Now we'll go to DC machines and continue our discussion. So we'll first understand the field in DC machine, which eventually turns out to be the most complicated electrical machine in that sense. In if try to be understood in field perspective, I cannot just simply explain that as I explained the synchronous machine or the induction machine. You will see that we have to go into some details of the winding, how we are connecting it to certain things and other things. But yeah, then we would realize the equivalent circuit, electrical equivalent circuit of the DC machine. We'll go into modeling and subsequently continue with controller design and other aspects for that machine. And because we had comprehensive introduction to all electrical machines, so the same concepts uh, that uh, I'll be applying there can be applied here also, and inductance equations and other things can be written for these three-phase machines also. That is beyond the scope of the present course. In future I may take up that, but as of now that is beyond the scope of this. Okay, so next day we'll start with DC machine and continue. Is there any question?
Yeah, Samrat, I have one question.
Yes.
For generators, the prime mover will be mainly of a turbine, right?
Yes.
Okay, so if they are connecting to some, power lines, the generator will be
Yes.
actually connected to power lines.
Yes.
So, uh, is there any supply that is given to stator, or it will be like only the outputting element?
No, the stator, as you know, that induction generator is not self-starting, so it requires some excitation. So there are different things like if it is connected to grid, that can be taken from grid, but if it is some passive, if it is a standalone generator, then you have to provide for some capacitive reactive power into the induction machine to start, in order to start that. Yeah, those
Okay,
issues
okay,
are often discussed in books, in induction machine courses. Yes.
okay,
So induction machine is not, you it requires, it needs a active source in the stator also for it to start, and then the prime mover has to take it beyond that synchronous speed, and then it will start generating.
okay.
Anything else, or will close?
Nothing from my side.
Okay.
Thanks.
Yeah. Thank you. Good night.
Thank you. Bye.